So in our next section here, we're going to start our discussion of the virtual port channel, or the VPC feature. And as we were mentioning before, this is a very large topic domain for Nexus. There's a lot of different caveats that we need to talk about, a lot of different designs that we can be using with the virtual port channels. But as we saw up to this point, what we were doing with regular port channeling is that we would be considering this what's known as a single chassis port channel, where the idea is that we have two devices that are trying to aggregate the bandwidth of their links together. So we have essentially one downstream device and one upstream device. So for example, an end host that's going to an access layer switch, like a 2950, 2960, 3500 series switch. We have two fast Ethernet links, and then we're binding these together in a 200 megabit per second Ether channel. Where again, the hard limitation of this, regardless of what the platform is that the flow cannot exceed the single physical bandwidth of a member link. So you do have to make sure that regardless what platform you're dealing with, that your load balancing method is set such that it does try to balance out the load between the links. And also, you do not need to set the method the same on all of the devices. It's an independent decision based on how the traffic is leaving outbound on the port channel. Okay, so originally this was just going to be between two devices. Now the advantage of this is that it increases the bandwidth. So as opposed to one fast Ethernet link, we have two fast Ethernet links, so 200 megabits per second as an aggregate. But the problem we run into is that it doesn't really solve the problem of having a single point of failure. That the switch that we're connecting to, if that access switch physically goes down, then we're going to be isolated from the rest of the network. So next, Cisco came out with the multi-chassis Ether channel, which is the MCEC or the MEC feature. Now, the idea behind this is that we're still going to have one downstream device, or basically kind of like the client of the port channel, but now we're going to have two upstream devices. So we could have our end host that's now going with two gig links to two Catalyst 3750 switches upstream. Where the advantage is, of course, that we're increasing the bandwidth because now we're aggregating multiple physical links together, but we're also adding some more resiliency and redundancy to the network, that if one of these physical chassis goes down, at least we're able to fall back to one of just the individual member links on its own. Now, from the perspective of the member of the, or I should say like the client of the channel per se, so from the downstream device's perspective, it's still going to logically appear as a two-device port channel. So if we have our end server that is doing NIC teaming between its physical links, and then it's talking upstream to a 3750, or excuse me, to two 3750s, from the perspective of the downstream device, it looks like it's attached to the same switch on the upstream. Now, in general, at least specific to Cisco's catalog, there's pretty much three ways that we can do this. Okay, the first, as I mentioned, is going to be with the 3750 platforms. And I believe also the 2960s can also do this now, some of the newer access layer switches. But the idea behind this is that we have the stack-wise configuration, which is essentially a backplane extension cable that goes between the switches in a ring on the back. And we can then do an Ether channel between two separate access switches, so two physical boxes that are within that stack. So I have two ports that are coming out of my physical server. One is going to one switch, one is going to a different switch. But from my perspective as the end server, I think that those two upstream switches are actually one physical device. Okay, the next iteration of this is then the Catalyst 6500 virtual switching system, or the VSS. Then finally, we have what we're going to be dealing with today, which is the Nexus's virtual port channel. Now, the basic theory behind all of the three of these is the same, that we're trying to combine the multiple physical links together in a channel, but the way that they are implemented in the StackWise and the VSS is a little bit different than how virtual port channels work. Now, the main functional difference is that in the 3750 and in the VSS, they use a single control plane in order to maintain the port channeled links. And specifically, StackWise does this via that stacking cable that goes on the back side of the switches. And the VSS does this by what's known as the virtual switch link, or the VSL. So the VSL is basically like two 10 gig Ethernet links that are plugged in between the two physical chassis, and that's used to synchronize the control plane information between the switches. Now, in the case of the virtual port channel, or the VPC, the main difference here is going to be that we have two separate control planes. So, for example, with the 3750 series switch with the Stackwise, when you plug the console cable into any of the switches in the stack, you're always going to end up on the single control plane command line of the master of the stack. Okay, the same is true with the VSS. Whether you're managing it from one chassis or another, there's only one supervisor at a time that is actively managing both of the chassis. Now, VPC does not work that way. We have two independent control planes. So if I have one Nexus 7000, a separate Nexus 7000 that are VPC'd together, if you have a console port plugged into one, console port plugged into another, they're completely separate interfaces. So they have different management IP addresses, they have different instances of the control plane protocols that we're running, and one thing that then becomes a potential problem is that they have two separate configurations that we need to manage. So in the case that the configuration on one VPC peer, or out of the two, the pair of the VPC devices is the pair, if one of the VPC peers does not match the configuration to the other one, then we can have some problems when we actually go to try to send the traffic in the data plane. So the key here then with the VPC, the configurations are going to be maintained independently. Okay, we also have separate control plane protocol instances, things like spanning tree, our first hop redundancy protocols like HSRP, VRRP, GLBP, any of our IGPs and BGPs, those are going to be separate instances. So from the perspective, ideally, of the, or I should not say ideally, but the end result, from the perspective of the downstream device, they are going to look like one individual chassis, one control plane, but really behind the scenes they are two separate control planes. And the way that they're able to accomplish this is by what is known as the peer link, which is used to synchronize the control plane between the two devices. So it's the similar logic to the virtual switching link via for the VSS, which is the physical cable that runs between the chassis. But the key is that the VPC peers are going to be managed independently from an actual management and a control plane perspective. Now, from a very high-level overview, we could break the VPC down into a couple fairly simple parts when we look at just what's the overall functionality of the feature. Okay, the first of which is going to be the two physical switches that we're actually doing the channeling between. Okay, these are what we consider the VPC peers. So the VPC peers are going to be the physical switches that are upstream of whoever we are channeling towards. Okay, we then have on the VPC peers, each of them have a peer link that's going to be a physical cable that's running between the different chassis. We have a peer keep alive link that's going to be a layer 3 interface that's basically pinging them back and forth to make sure that the peers are still available. And then we have the VPC member ports, where this is going to be the actual downstream facing interfaces that are going towards whatever the member, like the end server, or it could be a downstream switch, or maybe even a downstream router that we're trying to attach to the virtual port channel. Now, the end result of this, of the VPC from the downstream device's perspective, again, is that they are channeling to the same physical upstream device. So if we were to think about some of just the logical topologies that we could have here, if we were to have a downstream end server that has two 10 gig links, so two 10 gig links, they go up to either maybe to Nexus 5000s or 7000s or even the fabric extenders. We have then the connection between the 5Ks that is going to be used for the peer link, and we have another connection that is going to be for the peer keep alive, just to make sure that both of the devices are active. We then have the VPC member ports. So these are the links that are actually used to channel in the data plane downstream. But the logical result of this, from the server's perspective, is that we have one device upstream that is just channeling to us downstream. So physically in the network, the connections are going to be in a triangle, but logically, it's a point-to-point circuit that's between them. So the reason, again, that we want to do this is that we want to make sure that the end links that we're using are running in active-active. where legacy spanning tree, we saw that we have the root port that's forwarding, then we have our blocking ports. We want to make sure that we don't only send traffic out one link and then have to wait for spanning tree convergence in order to allow us to forward traffic on the backup links. So again, the idea is that we're able to use as many physical links as we want, either to the in-house or between the switches, and then we're going to have some additional control plane protocols to make sure that we're not causing any type of layer 2 or layer 1 loops in the network. Okay, so again, our three major portions that we have of the VPC for each of the peers. So we have the peer link, we have the peer keep alive link, and then we have the actual member ports going down to the destinations. Okay, now the main goal of the first of these three, the peer link, is to synchronize the control plane information between the VPC peers. And the reason we need to do this is that if one of the peers were to learn a MAC address or to learn about a destination that is trying to receive a multicast frame with IGMP, or a layer 3 destination that we have our IP address to MAC address resolution with ARP, we need to make sure that both of the physical chassis are able to have this information. So even though it is two separate control planes, we're going to be using this peer link mainly to synchronize the control plane information between them. Okay, the way we do this specifically is with the Cisco Fabric Services Protocol, the CFS that we talked about previously. And in the case of VPC, we're running this directly over Ethernet, which then implies that the peer link must be a layer 2 link between the devices. Okay, it's going to be a directly connected port channel, actually multiple physical links between the devices. Now, the peer link is also used to perform an election that is for the VPC role, where we only have two physical devices in the VPC peers, so VPC peer primary and secondary, where the primary is used mainly to synchronize to start the synchronization of the control plane, and then to control what is the state of the links on the secondary device. And we're going to get into this in more detail exactly why we need the primary, secondary, and then what specifically these devices are going to do. Now, a key point about the peer link is that it is not used in the data plane. So it is mainly used just for the control plane synchronization between the devices. And the reason that this is so important is that the aggregate of the bandwidth of the peer link is generally going to be much lower than the aggregate of the bandwidth of the actual member ports. So for example, if we were to take a look at our physical topology here, we see that we have the 7Ks that are going down to some downstream devices. So if we look here between the two of them physically, we have these two 10 gig Ethernet ports, our two 10 gig Ethernet ports. Then assuming that we have multiple members that are going downstream, the problem is that this link that's used between them, which we're going to be using as the peer link, it could potentially get saturated in the data plane if we have lots of downstream devices that are basically going to be the VPC members. So we want to make sure that based on the specific design that we are doing, that the peer link is used for just the minimum amount of traffic possible in the control plane. And there are certain cases where there are failure scenarios, or if the network is improperly designed, that the peer link will be used for the data plane, and that's really not the ideal case for it. Okay, so the main issue is why we do, the reason we don't want to do that then is because the peer link becomes the bottleneck of the network. Okay, so we'll come back to this in a little bit and get into more specific details about why this is bad. Okay, we then also have the VPC peer keep alive. So this is going to be a layer 3 interface that is going to use basically a UDP ping to figure out that both of the devices are actually currently running the VPC process. So if one of the devices crashes or there's a link failure, the peer keep alive link is going to tell us that based on just that UDP ping. Okay, this is also going to help us prevent a situation that is known as the dual active or the split brain in the VPC roles. And we'll see that this becomes a big design consideration, and a potential failure problem that we can run into with VPC is that since there are two separate control planes in the devices, so each VPC peer is running its own management protocol, it's running its own spanning tree, it's running all of its other own control plane protocols, that if the VPC peers are not able to communicate with each other and they accidentally both elect themselves as the primary role of the VPC, the end result can be that there's a failure in the forwarding in the data plane. So it's a really important point to make sure that we do not run into this situation, which is the dual active or the split brain situation. Okay, now the peer keep alive link is not used in the data plane in any situation. The peer link we'll see could potentially be used in the data plane for VPC, but the peer keep alive link is not. It's mainly used just for this UDP packets. They're unicast packets at port 3200 that are basically just pinging back and forth to make sure that the devices are still there. Now, there's a couple different design options we'll see for actually configuring the peer keep alive link. One of the options is that we could use the management 0 port that's already built into the platforms. So we'll see once we get into our configuration examples here. One of the most basic examples is when we're doing the VPCs on the Nexus 5Ks. We can use the management port as the basic keep alive between them. Once we get up to doing this on the 7Ks, the design becomes a little bit more complicated, where you normally would not want to use the management port because you can run into some problems with failure situations and dual supervisors. And we're going to come back to that and talk about that in more detail when we get into more of the specifics. Okay, the link also could be here just any layer 3 routed link or any layer 3 port channel. So it could be a cable that's plugged back to back directly between the devices. It could be something that's actually going over your layer 3 routed infrastructure. So it theoretically can run in the normal in-band network, so your normal in-band IP routed network, but ideally it's going to be some sort of isolated link that's back to back between the devices, or if it does go to the routed infrastructure, that it's going to be in an isolated VRF to make sure that it's used just for that particular purpose, just for the keep alives. Now, the last portion then is going to be the actual member ports that are used in the actual data plane forwarding down towards the final destinations. Now, for each of the VPC peers, they need to have at least one member port per virtual port channel. So these are going to be the physical links that are facing downstream towards the destinations. So we can have more than one, and the hard limit is going to be based on the specific hardware platform. Like in the case of the Nexus 7000, some of the M series cards can do 8 channels, some of them can do 16, some of them can do 32. It really just depends on the specific hardware that you have. So for details on this, the best thing is to do is to look at the release notes, because as the new modules are introduced, as the new software versions are introduced, this type of hard limit is changing. But the key is that you can have one or more members in the channel. And as you can imagine, the more members that you have, the more aggregate bandwidth that you have, and then the more redundancy and resiliency that you add to the topology. Now again, the key of the final logic of the VPC is that once the member ports are properly formed, from the downstream neighbor's perspective, the VPC is going to look like it's attached to just one upstream logical switch. So again, if we look at that physical versus the logical representation, where logically we have the point-to-point link between the server and the upstream 5K, the physical topology is actually a triangle connection of links, where we have one link going, or one or more, I should say, more links going upstream to the VPC peers. The VPC peers then have the peer link and the keep alive that are used to synchronize the control plane between them. Then these member ports, this is what's actually used for the data plane forwarding. Now, additionally, when we're talking about this within the scope of spanning tree, since from the downstream devices perspective, the link is going to look logically like a point-to-point link, it means that from spanning tree, we're not going to have any blocking ports. It's the same as if we were to have two access switches, let's say two 3550s, two 2950s, and they're doing port channeling together. From spanning tree's point of view, then, we're going to have the single port channel interfaces that are used as the forwarding ports, either the root port or the designated port. Typically, in the case of VPC, you would want your root bridge upstream towards the VPC peers. So normally on the downstream device, you would see that as the spanning tree root port, not as the designated port. Okay, another key point is that whatever the specific VLANs that are used on the member ports, so our actual access VLANs that are going to the servers or whatever we're trunking downstream, we need to make sure that those VLANs are allowed on the peer link between the devices. So even though on the VPC peers, the peer link is normally used just to synchronize the control plane, there are certain circumstances that it's needed for the data plane, whether we're using multicast traffic over the VPC, or we have a situation that is known as orphan ports, which means that they were previously members of the VPC that failed, or some type of device that is just single attached to one of the VPC peers. Now, one of the big issues we'll see once we get into the configuration of this is that VPCs are very, very highly subject to the order of operations that you put them in. So it's fairly easy to screw up this config, and once it stops working, it's fairly difficult in order to roll it back. So we need to make sure that we talk about what is basically the tried and true method of if you follow every single time, you should not run into any problems with the VPCs. Okay, the first of which is to make sure that we have IP connectivity established for the peer keep alive link. So whether this is over the management 0 interface or whether it's over some regular routed interface, we just need to make sure that the two switches, like the 5Ks or the 7Ks, can actually ping each other over some sort of layer 3 infrastructure. Okay, next step then is going to be to turn the features on. So VPC is off by default, LACP is off by default, so we need to say feature VPC, feature LACP globally. Okay, that portion is pretty straightforward. Okay, next we need to create the VPC domain, which is going to be a locally significant number between the two peers. So it's a number that does have to match between them, but it could theoretically be reused over and over in the rest of the network. And under the VPC domain, this is where we specify the IP address of who we're sending the keep alives to. So whatever destination that you establish the layer 3 reachability to, that's going to be used for the peer keep alive link, that's the address that we're specifying here. So technically, the peer keep alive is not a link per se, it's simply just IP connectivity between the devices. So it would be analogous to, like, let's say you have a BGP peering between two routers using the loopbacks. It doesn't really matter the physical infrastructure you use as long as they have IP connectivity to each other. And since we are using unicast UDP, the time to live of the packets is 16. You can't have multiple hops in the interim between them. But ideally, you would want to have them layer 2 adjacent, like either to a management switch or back-to-back links that are used for peer keep alive to make sure that you're not introducing additional devices' potential failure into the potential failure of the VPC domain. Okay, so we have the peer keep alive address defined. Next thing is that we're going to define what is the peer link. So the peer link is going to be a layer 2 trunk port that is a port channel that is specifically listed as the peer link. Okay, this is going to tell the switches what is the link that we need to run the Cisco Fabric Services over Ethernet, or the CFS-OE protocol, in order to synchronize the control plane between the two peers. And overall, this is really the most important link of the VPC. But if the peer link goes down, the VPC is not going to be functional anymore, and we're going to have to take all of the member ports out of the VPC. Then as a worst case scenario, we can ideally fall back to layer 2 spanning tree. So from a physical design point of view, when we're thinking of the redundancy of the network, this is one of the most important portions of the VPC. So if we're thinking of a VPC in terms of, let's say, the Nexus 7000, we know the Nexus 7000 has a couple different levels of redundancy. Okay, it has redundant power. It has redundant supervisors. It can take multiple line cards. So ideally what we would want to do is to have two separate 7K chassis that when they're forming these peer links, we'll say that we have not only dual supervisors, SUP 1 and SUP 2, but we have whatever the first line card is and the second line card. Okay, these could be M1s or F1s or M2, F2 ports. We'll talk a little bit about later specifically what the difference is going to be when we use different types of hardware. but we would want to make sure that there's a good distribution. Let's say this is line card 2, a good distribution of how the physical peer link is formed. So we would go maybe from line card 1 to line card 1 with 2 links. So we have 20 gigs there. Then we have an additional 2 that are going between line card 2 and line card 2 that are channeled together. Then the result of this is the logical peer link that is connecting the 2 chassis together. So the idea behind this then would be that if one of the supervisors goes down, we have stateful switchover that is immediately going to take over. If one of the line cards goes down, then we're able to still use the other members of the peer links channel to make sure that we can constantly synchronize the control plane between the devices. Because in cases where the peer link does fail, it can be a catastrophic failure not only for the control plane, but also for the data plane, where your servers could be physically cut off from the rest of the network because it's not able to forward the traffic on either of the peers anymore. Okay, so this portion is really important, how we establish the peer link. Okay, next is going to be to make sure that the member ports that we're going to use are going to pass the consistency parameter check, which would be things like, do they have the same speed? Do they have the same duplex? Do they have the same VLANs configured? So the normal parameters that you would take into account when you're dealing with port channeling, you need to make sure also to take those into account with the virtual port channels. Now, for this particular step, there's tons and tons of attributes that need to match between the devices, or at least be compatible between the devices. Luckily, you don't need to memorize it, though, because there's a really straightforward command that you can use on both the 7K and the 5K that's going to give you line item by line item what are the things that need to match, what's the value on this side, what's the value on that side. If you see a difference between them, then you just change them in order to match, and then you should be able to pass the consistency check. Okay, the final step then is we're actually going to apply the member ports. This is where we're going to go into the data plane down towards the final destination. So ideally, you would shut down the links that go to the members. You would then apply the VPC to the member ports, and then you would bring the member ports back up. Now, the only issue with this is that in high availability environments, if you can't schedule a maintenance window to add or remove links from the VPC, could be a potential problem. You don't necessarily need to disable the link, but there can be some weird order of operations problems that you run into, like a layer 2 loop, or the VPC starts flapping up and down if the links are not properly added in the correct order. So if you shut down all the members, add them to the VPC, then re-enable them, you're pretty much guaranteed 99% of the time that it's not going to have a problem. Okay, so before we get onto the command line, there's a couple different questions I think we have here. There's one question, can there be more than one keep alive port? Okay, yes, there can be more than one physical link, but there's not more than one logical link, because it's a layer 3 link basically. So as long as I have layer 3 IP reachability, it doesn't necessarily matter how the traffic routes physically between the devices. As long as you can do like an ICMP ping between the boxes, then your peer keep alive is going to work. There's another question. The member ports per VPC on the previous slide. Let me go back a little bit here. Each VPC peer has at least one member port per VPC. Okay, basically what this means, if we look at the physical diagram that I drew out here, is that if this downstream server, okay, so we have server 1 here. If server 1 is going to be attached to the VPC domain, okay, so these guys make up the VPC peers. This peer has at least one member link. This peer has at least one member link. So you need to make sure that the end device, whether you're channeling to a server or whether you're channeling to another downstream switch, you need to make sure that they are dual attached. There should be at least one link to each peer. There can be more, but there are cases that if we were to only attach this server, let's say this link didn't exist, if we were to only attach the server this direction, this is then what is considered to be an orphan port. And there are some strange failure situations you can run into with orphan ports that they can get cut off in layer 2 or layer 3 connectivity to the rest of the network. So ideally, technically it's not a requirement that you have at least one member port, but it doesn't really make sense to run VPC unless your end devices are dual attached. So you want to make sure that at least one member port per VPC peer. So that's the downstream facing link. There's another question. The Keep Alive link is just a heartbeat in the peer link to exchange the info of the peers. Correct. So the Keep Alive is just for doing the ping, basically. It's a UDP ping back and forth between them. The peer link is the one that's used to synchronize the control plane, the really, really important one. There are some cases where the peer Keep Alive link can go down and it's still going to be okay, but there is never a case where the peer link will go down and the VPC will be okay. Okay, we're going to take a look at some examples of that, of what are the different failure situations and what are the end results of them. There's a question, is it possible to form a VPC between two separate line cards? Yes, it is. So as long as it's within the same physical chassis, if you have two M cards and two F cards, and then you have another chassis likewise with two M cards, two F cards, you could channel between the two M line cards, you could channel separately then between the two F cards. And this is actually going to be the ideal design in order to use the M cards for the pure Keep Alive, because the pure Keep Alive needs to be layer 3, and then you're going to use the F cards for the peer link to actually synchronize the control plane and then use that as kind of a last resort in the data plane. There's another question, can the pure Keep Alive link send over the trunk of the peer link? Technically, yes. Technically, you could route the traffic of the pure Keep Alive link over the peer link, but you don't necessarily want to do that. Okay, the idea of separating the roles is that you have multiple levels of redundancy. That if the pure Keep Alive link goes down, or excuse me, if the peer link goes down, it doesn't necessarily mean that the Keep Alive link goes down. Because basically the catastrophic failure for VPC is that both the Keep Alive link and the peer link goes down, then the peers have no idea how to synchronize. Is one of them really up or is one of them really down? And that's how we end up in that dual active or that split brain situation. And we're going to take a look at this on the command line. There's another question, is there any requirement to connect a non-Nexus switch like a 4500 to a VPC specific to spanning tree? There's no special requirement. So from the downstream switch, if it's like a 4500, if it's 6500, it's going to look like a normal spanning tree connection. Okay, the one other minor difference here is that if your upstream peers are Nexus, which is always going to be true for VPC as of today, if your upstream peers are Nexus and your downstream peer is Catalyst iOS, Catalyst iOS runs a feature that is known as Ether Channel Guard that is used to figure out, are there some misconfigurations on the port channel? There are some cases that in VPC failure scenarios, the downstream Catalyst iOS device will suspend the port channel, which suspending the port channel means you fall back to the regular member links and then use regular spanning tree based on some basically misconfigurations of the VPC. But ideally, what we want to be able to do is set up the network so that the worst case scenario, we're going to fall back to spanning tree. We don't want the worst case scenario to be that the data plane is just completely broken. Because the goal of VPC is to get around that problem where I want one link going this way, one link going that way, but I want to be able to forward on both of them. I'm trying to do active-active. The peer link, there's a question, is the peer link a layer 2 only link for the F card? Technically, you can run the peer link on the M card as well. So you can run, technically you could run both the pure Keep Alive and the peer link on at the F cards only, but you would need an M card in the chassis at least in order to do the layer 3 routing, the layer 3 proxy routing. So there's a couple different designs that we can solve with it. Okay, so let's take a look now at the command line of how to do this, and let's quickly review the order of operations. So the first thing we need to do is get connectivity for the pure Keep Alive. So I want to make sure I can ping between the devices. Okay, next step is I need to enable the feature set, so both for VPC and for LACP. So I want to use LACP for my port channel negotiation. I'm going to configure the VPC domain, which is basically just a number, and then define what's the remote end that I'm trying to do the Keep Alive to. So what remote device am I sending that UDP ping to? Okay, then once I know that the peer is reachable, we're going to establish the peer link. That's going to start to run the Cisco Fabric services over Ethernet protocol. Once all of that basic control plane is set, Then we can move on to the final step, which is actually to configure the member ports going down to the final destination.